In this video, I'm going to go over an organic chemistry problem, specifically Fischer esterification. So in Fischer esterification, there are three ingredients. The first one is going to be a carboxylic acid. So let's say I have this carboxylic acid here reacting with an alcohol in acidic conditions. So let's say our alcohol here is going to be 2-tert-butanol, and our acidic conditions here is going to be strong acid, sulfuric acid, H2SO4. Right. So in short, what Fischer esterification would do is convert a carboxylic acid into a ester, right? Where to quickly predict the product here, we're gonna substitute this OH group of the carboxylic acid into the OR group of the alcohol, which will give us this ester right here, right? Where we see that this OR group here is the OR group of the alcohol right here. So this is Fischer esterification, where the mechanism is nucleophilic acyl substitution. The mechanism goes like this. In acidic conditions, the carbonyl oxygen will get protonated by the H2SO4 and give us this protonated and activated electrophile here, right? Because this weak alcohol here cannot attack this carbonyl-carbon right away. It has to become activated by protonation first, which then allows the weak nucleophile alcohol to attack the carbonyl-carbon, push the double bond onto the oxygen, and give us this tetrahedral intermediate right here, right? Which will then lead us to the proton transfer steps, where we're gonna deprotonate the group that we want to keep, which is this new group right here. And to do that, we're gonna use HSO4 minus to deprotonate the group, make it into a bad leaving group because we want to keep that group, as we see here in the ester product, right? And now once we have deprotonated that group, we are going to protonate this OH group because we want that group gone. We do not see that group here. So we want to make it into a good leaving group by protonating it with the H2SO4 that we reformed in the last step right here, right? Which is going to give us this intermediate right here, where to kick off this good leaving group that we just formed, we're gonna reform the carbonyl with the alcohol right here and push off that good leaving group, giving us our final intermediate right here, where we have our carbonyl that still has its proton, right, which is why it's positively charged, the OR group here, and the side product here is going to be water, which is the leaving group that left. Where the final step here is to neutralize the positively charged oxygen by deprotonating it with HSO4 minus, like that, which gives us this ester right here, right? So all of these steps here are reversible, because if you want to go backwards from an ester into the carboxylic acid, you can do so by adding more water in acidic conditions. So think of this as Le Chatelier's principle. If you add more alcohol, you're going to get more ester. If you add more water, you're going to get more carboxylic acid, right? And going from an ester to a carboxylic acid is hydrolysis. And I hope that helps. So if you want more help, comment any questions you have about organic chemistry, or join my office hours in the link in the bio.